Welcome everyone to our Tech Exchange seminar series of IAD. My name is Ranga Settler. I'm the Associate Director for Community Engagement here. The objective of this series is to, we will be recording these and we will have this circulated as well to our mailing list so that our affiliates can look at it. The objective is to try to see if we can generate collaborations across the university community. People find it difficult to sort of enlighten themselves about all of the various AI-related research that's going on across the campus. And one of the primary objectives of this is to get cross-department, cross-disciplinary collaborations going. And I think we've been successful in prior talks as well. We've had people after the talks sort of connect and engage and try to push things forward. And we hope that this will continue to happen. Next week, we had a conflict with the SUNY AI Symposium, so there won't be a Tech Exchange seminar series talks next week. We will send out an announcement. Again, if you talk to your colleagues in your departments, please let them know of this opportunity. And again, we'll sign people up for the fall. The spring sessions are all booked, but we will continue to do this in the fall. So we have two speakers today. Our first speaker is Nathalia ANDRADE from the Department of Periodontics and Endodontics. And we look forward to your talk.
Hi, everyone. I'm Nathalia ANDRADE. I'm faculty at the dental school at the Department of Periodontics and Endodontics. And I'm very happy to be the first one opening the Tech Exchange seminars. I think it's a very nice opportunity for people to understand what we do at the dental school, the innovations we want to bring to the dental school and work together to reach our common goals. So first I will show... Not working. Oh, yeah. So I asked ChatGPT to tell me what's the future of dentistry in an image. And the image it came out was like that. So they actually put a robot in the place of a dentist. I don't think it's that exactly what's going to happen, but I think it's pretty similar to the second image they gave me, where we're going to have robot assisting us to do the procedures with more precision, digital tools to help us analyze all the data we get from the patient. And I think that's pretty similar to what we're going to have. And I actually don't think that's that far in the future. I think it's a lot in the present. That's an image of a robot called Iomi. Is that too? Making some, that's better. That's the image of a robot that we use that assists us in the procedure. So in the background, you can see they have some digital tools, and that's the way we teach the robot what to do. And then this robot called Iomi connects to the handpiece, and it does not allow us to make a mistake. So we are forced to follow the plan. If we try to make any wrong movement, it's going to lock your movement. And that's something that's already there. It's already happening. So that's what I'm saying is not the future, it's the present. But there is one thing, is the present is just not evenly distributed. It's there, it exists, but not everybody have access. So since I started to work at UB around 1 year ago, 1.5 years ago, my goal is being to make all this technology more available for the students, not just in terms of having the structure at the school, but also making sure everybody have knowledge to know how to use these tools to their best, to the maximum potential. So today I'm going to show some of these innovations that I have been working to have at the dental school, in the clinic, for patient care, in education, in the course they give, and also for my research. So starting with the clinic, what's a gold standard for treatment today, and that's how we do at the Periodontics clinic. We take an intraoral scan of the mouth of the patient, and we merge that information together with photos and a CBCT scan. The CBCT scan is going to give us information about the bone. The intraoral is more the superficial tissues and the tooth, and the photos, the statics, the outside. And then we use AI-based softwares to merge all this information. It would be very hard for the human cognition to get all this information, all this data, plus the clinical data from the patient and come up with a treatment plan. So when we use these softwares, we can have all this information merged together in a way that's easier to visualize and to do a better treatment plan for the patient. So here, for example, we have the CBCT scan, that's the bone, that's where we see in the background with white and black. And then in the front, we have in red the nerve that passes through the mandible, so it highlights where the nerve is. And then we have a design of what would be the tooth that we are replacing. In this case, the patient missed a tooth, so we are replacing a tooth. And then with all this information together, we can place the implant in the right position. That's what you have in green. So the green lines is the implant in the right position, respecting the distance from the bone, from the anatomic structure and everything, and in the right prosthetic position to restore the tooth in the future. So that's what these softwares do for us. And then you also get a report with the information about size of the implant, position, and everything, and a 3D guide that we print. We 3D print, and then we use at the time of the surgery in the mouth of the patient and have all the guidance that we need to do the procedure. The same process of doing the diagnosis and the treatment plan is what we use to teach the robot the right position to do the procedure. And here I put the example for dental implant, but we also use for other kind of surgeries. We can also use AI to preview how the treatment is going to look like for the patient, and that's really good because the patient can have an understanding, a much better understanding of how it's going to look like, and the patient can discuss with us, oh, I like that, I don't like that. And we can also use these images to discuss with the other dental specialists when we need to work together in a case. And the images were AI generated by my students, Brian and Omar, during the course I give to them to learn how to use these tools. This will help us to speed decision-making because we don't think during the surgery where we're going to place the implant, where is the nerve, we already know that. So it speeds the process of doing the surgery too. It increases accuracy and it's proved in the literature, and it also improves patient satisfaction because it reduces the number of times we need to repeat procedures. You reduce the mistakes, so the patient is happy. And the patient is also better informed of what's going on in their treatment and what's going to be the outcome. The patients get more satisfied with that. And to do that planning that I showed, now what's happening recently is that we have AI tools to help us do that planning in a better way. So what it does, that's how the software look like to do this planning. And then you click there and you can ask to have the assistant too. So if you look at the top, we have the 1, 2, 3, 4, 5, up to 8. These are the steps we need to do. When we use the AI assistant, we jump from 1 to 5. And that reduces a lot the time that we need to do the planning. What before would be like 1 hour doing the planning, now it's a few minutes and you get it done. And for the dentist, that's great because, for example, some of my friends that work in private practice, they do this planning during the weekend or after hours. So if you can reduce that for a few minutes instead of 1 hour, it's actually great. And it's also good for the patient because it's more accurate. Until, I would say, a couple years ago or maybe a year ago, not many people were using the AI assistant tools in the software because it was not accurate. So AI would do and you'd need to fix. But now it's actually very precise and it's better than what we could do as humans. So it is more precise, it's good for the patient, and it's good for the dentist because we feel more safe that we're doing it right, and it's faster to do. And then I will show how some of these tools work. So in this example, we are connecting the CT scan, like I said, as the bone, with the intraoral scan, that's the superficial tissues. And we would need to give like 3 points of reference and then manually adjust. And that would take some time. While now we literally just click on time and it's ready for you. So that's how it's saving us time. Or it can also segment structures for us. So it separates each tooth and mandible from maxilla. So it's easier if we need to plan a case, for example, that we need to plan for multiple extractions and multiple implant planning. It's way faster. Before we would need more than one software to be able to do a planning like that, and it would take really a long time. It can also help us to find the anatomical structures. Like I said, there is this big nerve that passes through the mandible that we always need to take care. And then in the first part of the presentation, you can see how I'm teaching the machine how to find the nerve. So I'm pinpoint the pathway of the nerve. And then in the second video, you can see that it did that for you. You just double check if it's correct. And by my experience, it's always correct. Like I never got a case that AI did it wrong with the new softwares we are using. It can also place the implant for you, but that's the point, it's not doing it right yet. If you look careful there, you see that the implant was placed in the wrong position, it's actually outside the bone, and we need to change the angulation, we're moving the angulation. So here is one area that I think would be really interesting to work together with computer science, with engineer, because we still need to improve the softwares. It cannot place the implant in the right position. It cannot also choose the right implant for that case. So that's a knowledge that's still depending a lot on the dentist. Now I'm going to show a little bit of education. Like I said, I really want the students to know how to use the software. They were available at the dental school, but they were not being used to its maximum potential because a lot of people just didn't know how to use. A lot of the faculty didn't know most of the faculty didn't know how to use. So we did this course that was for all the residents and also the faculty were attending to learn. And I had AI seed found from CAT, and then with the found, I was able to bring experts from other schools to teach different techniques that we didn't know. So here are the photos of some of them that they brought this knowledge. And they are also from schools that they already have this flow established in larger scale. So they were helping me to understand what was needed to do at the dental school for us to establish that as the standard care for all the patients, not just for a small group. And then the students had hands-on and simulation activities. They also had microsurgery training. And we developed didactic materials. The didactic material developed is not just teaching the technical part, it also teach like where to click, what to do, but it also is incorporated in the material, the critical thinking behind. So before you click this button, make sure you remember all these concepts that we review in class, that you learn through dental school, and put all that knowledge together before taking that decision. It also teaches the limitation of AI, like what AI can do and is really good, go ahead and trust, and what you cannot trust yet, make sure to use your critical thinking to take that decision before you click. And this is another activity I also did with the students that was in collaboration with the Dental Tech Club. That's a club that, done by the students. And then we did the AI immersion experience. So it was 2 days training. We brought a robot I showed in the beginning for the students to play and understand how it works. They also had lecture with me to know how to do the treatment plan. And we did a partnership with Straumann. That's the company behind the software I showed. And then they brought their own computers for the students to have training on that. We had a few sections of them full of students. I was trying to make fit everybody, but it was not easy. But we did the training. And then they had a chance to play with the robot and understand how it works all together. If we do the planning, how the robot would behave. And then they had a simulation with a fake block of bone that they could drill like they were doing the surgery. And here's just another view. Here's a little bit about how the robot works. You see in the second video that if the mandible moves, the robot moves together. So it really does not allow you to do any wrong movement, and it follows the patient face. And all these activities I showed, they got some coverage from the media, from UB, and even from TV channels outside. So if you search my name on Google, you can probably find more information about all these activities as they were happening. We were getting a lot of attention that I didn't expect, but it was nice. And here are some of the things I want to bring in the future. So I went to this conference. This was in Singapore, and it was the conference from the company that have the software I showed. They're really in the front regarding implementing AI for dentistry. And then they have this, they're developing this training using augmented reality. And here you can see that you have the control on your hand, and then you get the feeling on your hand of what a surgery would actually be. And I tested, and it's actually so realistic. It vibrates in a way that feels like you're drilling a bone. That's what we'll do for the surgery. So that's very nice. And also the whole environment in the augmented reality is like you are doing a real surgery, and the person that's assisting you, I don't know if I can say the person, yeah, the augmented reality person that's assisting you, is giving you instructions like an instructor would give to you. So if the angulation that you're drilling the implant is wrong, it's going to help you to correct the angulation, and it's going to give you indications of what's the right movement to do. So I think it would be nice if we can actually develop that here and have our students having that here. At the same conference, the classrooms were like that. And I really think that's the future, having augmented reality so you can visualize better, especially for dentistry. Dentistry, like I said, we are very visual. We need to put a lot of images together in our mind and combine that to do the treatment. So I think that's really nice if we can bring that for our teaching at UB. And now I'm going to show a little bit of my research and some of the collaborations. And here I also want to mention some of the opportunities for people to work together with us. We are actually looking for people that can help us with the engineer part of the ideas we are having. So that one of the projects I'm doing together with Dr. Thalita Vieira from Oral Surgery, we are putting together the surgical specialists of dentistry to try to come up with new solutions, especially in teaching. And that would be a mannequin that is connected with AI assistant that can give feedback to the students. So for example, you're doing the right pressure or you're going the right direction. If it's giving an anesthesia, I'll go to the right, go to the left, or this is right. So we want to give that to the students. We feel that sometimes, especially for the surgical training, is a lot of pressure for the students if the first time they're trying is directly in a patient or in a colleague like we normally do. And it's also stressful if they're getting feedback from the faculty judging them, like, oh, this is wrong. So I feel the interaction with a machine could make that learning process easier, especially for surgery that's already a stressful moment for the students. And like I said, sometimes the patient lost the tooth and we replace with implants, but my specialty is also about saving the tooth, not letting the patient get to the point of losing the tooth. And one of the main diseases that make patients lose tooth is called periodontal disease. That's an infection that happens around the tooth. And then you have bacteria that attach to the tooth surface. And then as our body starts to try to fight against the bacteria, instead of eliminate the bacteria, that does not happen, it causes damage around the tooth. So you lose bone and you lose the tissues around, like the gum tissue get affected. And then if you don't treat or if it's too aggressive, the patient ends up losing the tooth. So doing research, so to get the diagnosis of the disease, we need to analyze images like everything in dentistry, and we need to analyze the X-rays and also some clinical measurements. And I'll have some AI based software that help us to do this analysis that takes some of the measurements for us. And these are images of a software called Overjet, and have other ones, have Pearl, have a couple more. I tested all of them. They're really nice, but they're still very limited in terms of giving the diagnosis. They're not that precise. And also they tend to overdiagnose. You get an overdiagnosis. And I try to work with some of these companies to make it more precise, but they don't want, because financially is actually good that they overdiagnose. So I think as a school, we have, it's on us to create a software that's actually reliable regarding the diagnosis. So we want that to be more reliable, and we want that to have the standards that we use in our clinics, so we can have the softwares in our computers helping our students and helping our patients. So one point of research that we have been working on that. So the first step would be to have a data set to do the models. And then I'm working together with Dr. Renato Casarin. He's from the same department I am. And we are finally having a big data set of photographs, X-rays, perio chart that have the measurements around the tooth. So we are ready to start to run the models, but we don't know how to run the models. So that's one of the points that would be really nice to have collaboration with someone to start to develop that. And the last part I want to talk about is how we use AI for genomics. And that's actually one of my main areas of research. That's what I have been doing my whole life. AI came in the last years and more as a hobby, and now it's becoming my main thing. But what I actually do is immunology and molecular biology. And one way we can study the periodontal disease is by taking a little piece of tissue around the tooth and exploring how the cells are reacting to that disease. And then we do that through analyzing RNA sequencing of the cells. And then as we we process the cells, we use a lot of AI tools to read, because if you imagine we have millions of cells from many patients, different spots on each patient, and then we have data sets from the whole world because these data sets become public. So when you want to do analysis of all that, it's really a lot. So we need AI to be able to find patterns and to understand better how all this information could turn into actually a treatment. And then that's one example of the research I do. I'm not going to go in deep on that, but basically I'm looking at the cells, all the immune cells, and I'm seeing the different expressions of genes that I know will be important. And then AI help us to visualize all that. Get all this information without AI would be really hard to visualize and understand what specific cell and what specific gene could be the target. So that's one of the ways we can use AI also. And just I'm thinking that AI is reshaping how we do research, and I see that a lot for my research, because now it's
basically you want to get a single cell genomic information for different key at different location, right?
Yeah, so for my research specifically, I believe one of the, I studied cancer before, and I just correlated that one of the proteins I knocked down for the treatment of cancer could work in periodontitis because it would affect the immune cells around the periodont. So I'm looking all the pathway of that protein, and I'm looking all the immune cells to understand what cells have that protein that I'm looking as a target expressed or not. And also that's what the next thing I would mention, that when you want to use AI for your research, I think you need to understand how AI works. And at least for that, it's really to find a pattern or to do a comparison. You cannot go beyond that on the research, on the answer you're going to get. So I include AI on my experiments and on the design of my experiments to answer questions that are regarding comparison. So if I want to know if one cell have more than the other one in expression, AI is a good way to know. If I want to know in that pathway of genes, of proteins, which one gets higher, which gene get higher expression, I can understand which cells would be a better target. But it's to give a hint, and then you do the other experiments to explore. So my idea today was not to show the whole research project, because I would be here the whole 30 minutes speaking just about that one, but was just to show that we can do that. And the main thing I want to talk about is that you start to think about your research design in a different way, because now you know you have a tool that can help you to do these comparisons and can help you to find these patterns that we didn't have before. And at least I'm seeing a lot in some research presentations I'm watching, and including at the dental school, some people frustrated and saying that they don't like using AI, that AI is not helping, or you can trust. I don't think it's that the point. I think some people don't understand what is the AI can help you. It can help you, like I said, doing a very good comparison when it's a lot of data that's hard for you to compare in another way. It can help you find a pattern, and then you need to use your understanding of science to understand what of the patterns could make sense to treat the disease you're looking for or whatever solution you're looking for. But I think what's important when we teach about AI, just like in the clinic, I teach the students what are the limitations and what they need to do by themselves. I think in science is the same thing. People need to understand what moment to apply AI, how to apply to get the best of it. And another thing that's changing in research is that I think more than ever, we need to collaborate with different people, different groups that we would not collaborate, we would not think about collaborate before, or would be very limited. I think we are opening. Dentistry tends to be a very small group, very close group, and I think we really need to open. And that was the main idea of my presentation today, show a little bit of what we do and what could fit, have other people collaborating and helping with us, giving a different perspective, different ideas. I always tell my students there is no way back. We are not going back to how it was before. There was a time in dentistry that we didn't use gloves, and that was considered nice. Having blood in the hands were considered you're a good surgeon. And nowadays, nobody would even think about touch a patient without a glove. So I think it's the same with AI. There is some resistance, to be honest. And on the other side, there is also people that want to know that and don't have access to the information. So I want to make sure we provide this information. I want to make sure we are in the front of this evolution and this innovation. We are not just using what's out there, but we are also developing that at the dental school. So that was it. That's my email. If any of the projects it's interesting for you and you want to be part of them, you can email me if you have ideas, want to brainstorm ideas together. We are also open for that. And I'm open for questions now.
Thank you. That was a very interesting talk. So any questions?
Thank you. I have another question. Even let's say we want to collaborate, right? Because of you, there's a lot of vendors, as you can see already, have this technology. They have a lot of kind of, they're already in the market, right? They build the software, they're not the open source. And even we develop something and how to integrate it with the current solution, rather than just we have to develop the solutions from the beginning. So how do you address this kind of challenge?
Yeah, I think there are two pathways. I think one path is actually working together with the industry because they also want to get better. So if we are offering a solution that's going to make their product better, they want to collaborate with us. There are many ways that the product can get better. Like I showed in the beginning, place the implant in the right position. None of the companies were able to develop that. Or even for the other one, I showed they overestimate, but they are working like a general dentist, the softwares. They cannot get to the specialty level. So if we could teach the software to do things that are deeper, they would enjoy and want to work together with us. So I think that's one path. And I think the other path is also developing things that we know are important. Maybe the company don't think it's important, but we know it's important. And the dentists out there also know it's important. So they would want to have access to a software that could do that, not just go with what is important for the company. I think that's a challenge in science in general. Like for dentistry, we have grants that come from the pharmacology industry and support from the pharmacology industry, but then they want their own way. And we don't stop to do our research our way just because the pharmacology industry can go faster and have more money. We do what we know it's right. So I think it's the same thing here.
So I think just following up on what Jinjin mentioned, so the data that you had, like when you showed some radiological data, and I'm presuming that some of the tools are well integrated into the processes. The others are maybe like you're just sort of inputting radiological images and trying to do certain things. How easy is it to get access to that data? Would you be able to?
I have been working on that because so we need to get RB approval, but it's not hard to get access to the data. It's the dental school is open for that. The IT of dental school is open for that. We have been working together in the last year to get to that point that we can use the data. Some of this data is also from other countries, like I'm from Brazil, so we have collaborations with the dental school there. And then the patients that are part of this data set are patients that already agree to have their information being used for research if it's anonymous. So you don't have access to the name of the patient, nothing that could identify the patient, but you have access to the clinical information that actually matters to develop the models to do the study.
Thank you.
So I'm a biostatistician, by the way. So my question is aimed along that line. You spoke about in your example, taking an image and letting AI bring together all the data so that you can come up with an optimal plan. And in your talk, you said more precise and better outcomes. But do you have like data to validate the word more precise and better outcomes?
Yes, I'll give one example, one practical example, but you can apply for other things. So for example, we have patients that we have the information about when the patient arrived, during the treatment and after the treatment, and we already know the outcome of the treatment. So we could have an analysis, for example, of what the different treatments we did, what outcomes they led, and what's the best way to do. And then let's apply this best way to do for the next ones. Or patients with a certain biography, they get this result or the other result. So we can do this analysis.
What I'm really thinking of is you also mentioned quite a lot of people in your area are resistant to using AI. And so how would you use data to convince them, you know?
Yeah, I think I would say some people are resistant because, like I mentioned, AI for certain spots, it still make mistakes. And for certain things, it's really good. It's better than what we can do. So what I think people need is to get more knowledge about how AI works and how you can use. Who is resistant is normally because they didn't understand how to use. It's not because they don't believe it's going to work.
AI is improving standard of care. Is that correct?
Yes, it is. And I tell this story to my students when I was choosing what school to do, and I decided to do dental school. I went to a dental conference with my mom. She's dentist too. And then there was one stand that was showing exactly that digital planning I showed in the beginning of that. That was 15 years ago. And then I pointed to my mom and I said, oh, this is so nice. I want to go see. And she's like, no, forget about it. This is not important. It's too expensive. It's never going to be a thing. The way we do is so much better. And that's it. And now 15 years later, I teach about that. And we actually do that at the dental school. So I think some dentists, maybe with AI, they think the same way, like, oh, the way we do is good, is working. Why would we use that? It's so expensive. Like have a robot in the clinic. I have one dentist in Buffalo that bought a robot to use at his practice, but like it's one dentist. And then when the students saw the first question, they were like, oh, this is so expensive. Like it's worth to learn. Are we gonna have that actually available? And I believe yes. And it didn't take 15 years, but it was 15 years ago when I was listening, like don't even pay attention on that. And the stand was completely empty to now that everybody's there using the goggles, learning how to do. I don't think it's gonna take that long until that become reality for all the dentists because now it's going way faster, the whole innovation process. So I think the dentists will be open for that. And that's a group of dentists because actually most of the people, especially for the clinical setting, they are way more open to use and they want to learn how to use. And they're taking very expensive courses outside to try to learn a little bit of what the students are learning here. So it's happening and they want to incorporate that. But I agree with you. If we have strong data showing how AI can improve the quality of care, that would help with the acceptance.
Just a
Yeah.
Talk about overdiagnosing in one example, right? And just a quick comment how to address that is really looking at your current standard of care, overdiagnosing, and maybe correcting for that bias. Because there's no way you're going to get a software company to deflate their diagnosis parameter.
I agree. That's what I want to do here. I think we are close together down here.
Yeah, let's thank Nathalia again.
Thank you.
So our next speaker today is Professor Bibhu SAHOO from the Department of Electrical Engineering. And yeah, go ahead.
One thing I can answer your question that it. Okay. So is this the pointer? Oh, here. Oh. So how does it work? Is it on? Yeah. Here. Is it okay? Can you hear me? Okay. So good afternoon. And I don't know, as I said earlier, it's a coincidence or something. 2 weeks back, AI really helped not drill one of my tooth. So I'll be talking about the engine that drives the AI. And I think it's the hardware that drives the AI. Software is also making things happen. So, so I'll be mostly talking about, I'll be showing 2 demos. I wanted to show 3 demos. And as usual, Murphy's Law came into place. And one of the things didn't work out right before this presentation. So I have only 2 demos to present. So, so as you know, AI hardware is there in almost all of the laptops that you are buying these days. The cell phones have neural accelerators. And a lot of the cameras have something fancy in there to process your images. So I'll be talking about 3 different hardwares. And I wanted to talk about one more, but in the interest of time, I try to limit it. And I will go over the block level implementation rather than any of the circuit details because it will be too much for the crowd over here. So first, I'll talk about the adder-only energy-efficient inference engine for edge devices. Next, I'll talk about a transform domain approach. How do you do a transform on an image and then do an AI on it to reduce the power? And then finally, I'll talk about how AI can be used to enable the software-defined radio and to give you more security. So that means the cell phone that you're carrying can on the fly detect what kind of modulation is coming onto the system, and it can reconfigure the modem to decipher that signal so that you can communicate securely. And in fact, the transmitter can also change the modulation scheme as they want, and the receiver can adapt to it. So these are the 3 things. I have a demo for the first one and the demo for the last one. Demos are 4 minutes each, so I might exceed a little bit if that's okay. Okay. So, oh, I use this, right? Okay. So this work was my first work. We did it in 2021. It got published in 2023. So what we do is we try to make sure that the whole hardware, not only the inference engine, which is the CNN or the SNN, that is not only low power, but the signal that gets into the CNN, either an image pixel or any kind of an analog signal that gets into the CNN, that also is energy efficient and it works in a much more energy efficient manner. So the first thing is we usually use 8 bits per pixel when we capture most of the images that we use. And if you look at the data sets that are there, ImageNet or any other data set that's CFAR10, they all use 8 bits per pixel per channel. When I say per channel means RGB, red, green, and blue. So what we are doing is we are using 3 bits per pixel. It doesn't work, right? And okay, no, I don't want to advance. I wanted to point. No pointer here, right? Okay. So we will also, one of the major computing operations in an AI accelerator is multiply accumulate, which people are trying to get rid of these days by using 1-bit weights. So what we did back 4 years back was we replaced the weights with only powers of 2 weights so that we don't have to do any kind of multiplication. It's just additions that we do. And then finally, we reduce the number of multiplications. In fact, in this case, it's only additions by reducing the number of filters that we're using by using pruning. Okay. So as I mentioned, generally images are quantized to 8 bits per pixel per channel. And that's there for most of the images. So what we do is we use low bit precision images, and that require usually an image sensor is there, and that is digitized by something called an analog to digital converter that takes in the analog signal, converts it into digital, and then transmits it or stores on the memory. So what we do is we digitize that image to only 3 bits per pixel. So that reduces, that does 2 things. First of all, it reduces the power consumption of the ADC, which is the analog to digital converter. And keep in mind, the power consumption of the ADC is an exponentially growing function. What it means is that if I have a 4-bit ADC versus a 5-bit ADC, the 5-bit ADC typically burns twice as much power. So therefore, if we reduce the resolution of the ADC that we are using to digitize the pixels, by even 1 bit, we save half the power in the quantizer. Next thing that we do is once we reduce the number of bits, now that bit has to be transmitted to the memory or to the processor. Now that means that is transmitted using a communication link. It can be a wireline link like an Ethernet, or it can be a wireless link. So now reducing the number of bits also reduces the amount of energy that is needed to transmit that bit, either in a wireline fashion using Ethernet or wireless fashion using RF. So there are 2 things that we achieve by reducing the resolution of the images that we digitize. So here we are showing, just to show that this rationale makes sense. So I'm comparing 2 sets of, from the CFAR10 data set, I've taken roughly 5 images, And what we are showing is that if it's quantized to 8 bits versus 3 bits, a human eye can recognize it. So at least we can say that what a horse is a horse, a car is a car. So the machine can do better also. And that we quantified that number by showing that with 3 bits, we hardly see any degradation in performance, 3 bits per pixel. And that results in 2.67x improvement in I/O bandwidth. That's what I talked about. When you transmit signals over the wireline Ethernet cable or over the wireless network, you save 2.67, which is 8 divided by 3. Then 32x improvement in power consumption of the digitizer. Why 32x? Because you reduce the resolution from 8 to 3 bits, which is a 5-bit reduction. So that means 2 to the power of 5, which is 32-bit reduction in the amount of energy that you would consume in the analog to digital converter that digitizes the image pixels. So next thing is, we did something fancy with the weights. The weights that are used in the CNN network, we quantize them into powers of 2. And the way we quantize them, they are having values between 2 to the power minus 1 to 2 to the power of minus 7, and plus and minus of that range, and a 0. Now, that results in 15 unique levels, first of all. And secondly, now we don't need, this is an 8-bit number. 2 to the power minus 7 is an 8-bit number. Plus the sign bit, it becomes roughly a 9-bit number. So we don't need 9 bits to storage that. We don't need to store everything. We need to only store the exponent, which is plus minus 7. So therefore, we need only 4 bits to store the overall weight. So therefore, we reduce the memory requirement by 50%. And then, as I mentioned earlier, so we did the pruning of the weights to make sure that we have minimal number of weights, minimal number of multiplications, additions to reduce overall power consumption. In fact, this work won the 3rd position in the world in the International Workshop on Logic Synthesis in 2021. So we presented this idea. We did this with the least number of logic gates to realize this whole convolutional neural network with least number of logic gates. So can you please play this video for me? So this is a demo of what we have done. And then just to mention, RTL stands for register transfer logic, which synthesizes the logic. Yeah, go ahead. Please play it. I'll speed it up so that we can meet the time. This one it's classifying as an aeroplane. So, because there is cloud in the background, so it thinks. So just to mention, so that whole thing is demonstrated on a field programmable gate array. It's a reconfigurable chip that you can program it on the fly also. But and the hardware that is inside that block is the overall block diagram is over here. It's a 7-layer VGG network, VGG7 style CNN. But we cannot program the whole network onto the FPGA. So what we did is we programmed one layer onto the network and use that. The processing core is one common processing core. We stream in the data. It goes into one of the RAMs, does the computation of the first layer, stores it in the second RAM, and then the second layer computation happens where that becomes the input RAM and the next one becomes, so it's in a ping pong fashion, it works that way. And the overall details are given there, how each of the bit widths at each of the points, how they grow, and how the multiplication is replaced with nothing but a barrel shifter, which is the greater than signal that is given there. So that's a barrel shifter. So there is no multiplication at all. Okay. So the next one that I'll be talking about is variable resolution pixel quantization for low power machine vision application on the edge. Here, this one I tried to create a demo, but it didn't work out. So this one is more on, we take an image and we take the transform of that image. So, and there are various transforms that are available that commonly used in image processing. We chose one of the transforms, which is very easy to realize in analog circuits, using analog circuits. Because it's, if I go for any kind of Fourier transform, Haar transform, or wavelet transform, the weights, the multiplications that happen are either √2, irrational numbers and all, which are very difficult to realize using capacitors and resistors. So what we are doing is we are using a transform called a Hadamard transform, which is a ±1 weights. So therefore, all it needs is addition of signals and subtraction of signals in analog domain. So I won't go into the math of it. It does a matrix multiplication. And this is the left side is the conventional architecture. You have the CMOS image sensor, which stands CIS, stands for CMOS image sensor, followed by an ADC, then the digitized signal. So what we are doing is we are going through a CIS, but an analog signal compression using the transform domain architecture, then doing a variable resolution quantization, and then doing the, after that, we are doing this neural network processing of that thing. So when we take the transform of a signal, so this is a nice image over on the left side, you take the Hadamard transform of that, and that's how it looks like if I take a 4-point Hadamard transform. It looks like these horizontal lines are there. So now what happens is that the reason we do that is because after I do the transform and take the statistics of the pixel values, amplitudes, you can see that it's a 4-point, so there will be 4 different outputs. The first channel will give you the weights, the image pixel values will be distributed all across, uniformly distributed between 0 and 1. I'm normalizing all the image pixels. But the second, third, and fourth channels, the amplitude of the pixel values are significantly compressed. They are compressed, they have a very small range. And since they're compressed, that's an image compression technique. You can throw out some of the bits. And therefore, that means therefore, we can ignore either channel 2 or channel 3. That means I'm digitizing half the amount of signals. And that's a significant savings in terms of power that we can get. I won't get into this. So this is the overall architecture. The CMOS image sensor is there, and then the overall thing. Our chip didn't work, so we had to go for in the interest of time, I'll skip these slides. We went for a COTS component, commercial off-the-shelf component-based demonstration of this whole idea, where we emulated an image from a CFAR10 dataset or an ImageNet dataset by taking that image from the dataset, convert using a DAC, digital to analog converter. We convert that signal back to analog and then pass it through an analog Hadamard transform, which is realized using resistors and op-amps. And this is all at the board level. So I'm thankful to the student who spent a lot of time actually making sure. It took quite a while to take these measurements because it is very slow. COTS component, they cannot work that fast. If it was an IC, then it would have run much faster at hundreds of megahertz. So it took a while. So these are the COTS components used. And interestingly, as you can see, what we did is we could do the quantization with only 3 bits per pixel, which is the third one, the E. The cow almost looks like a cow. It doesn't look very great, but at least the CNN can figure it out. And what we found out was that with 3 bits per pixel, BPP stands for bits per pixel, the third last row, you can see 7050. What it means is the 4 channels, first channel is quantized to 7 bits, second channel is ignored, completely ignored, third channel is quantized to 5 bits, and the fourth channel is again ignored. So half the signal is digitized. And that too, one of the signal is digitized to a lesser resolution, reducing the power, and we get close to 90% accuracy. Now, there is an interesting trend here. If you see that right column, the accuracy with a high resolution, 6 BPP, is 87% and 90% with lower resolution. That's where the noise comes in. That's the beauty of noise. When you quantize to low resolution, you add something called quantization noise, and noise actually helps you extract more information from a source. And actually, that is one of the beauty that we use noise in a lot of our circuits, and we call that noise as dithering. So we can dither a signal, analog signal, by adding noise, and we can recover signal, dig out the signal from there in a much more energy efficient manner. So this is just to show that it works with 3 bits per pixel. We get significant accuracy, significant reduction in power. Now, the last part covers a different domain, which is how do you build cell phones that can automatically reconfigure based on the modulation. Especially, it is very useful in electronic warfare. If they're in a hostile zone, they have to communicate. They can change the modulation scheme on the fly and make sure that it can reconfigure itself, and you can talk to each other in a much more secure way. So automatic modulation recognition has been present since 1998. Okay, and CNN has neural network have been used since 1998, but now it is taking off. Since 2016, there has been a lot of interest in this domain, and they have developed 2 kinds of data sets called Radio ML dataset 2016 and Radio ML dataset 2018. But all the work that happened in 2016, 2018 were all GPU based and some CPU based work. So last 2-3 years, there have been some work on how to realize that on an ASIC. So the problem statement is as follows. Assume an unknown information source whose information is modulated by an unknown modulation scheme. You don't know anything about what is happening. The set of all modulation schemes is known. These are the set of modulation schemes. The modulated signal is sent over a noisy wireless channel via transmitter. The signal is received by a receiver. The goal is to identify the modulation scheme using the received signal. And this must be done for varying noise levels, because you might be in a hostile environment, a lot of trees, a lot of buildings, signals bouncing back and forth, corrupting the signal reception. So that's a very low SNR scenario. And there can be high SNR scenario where you're in the open field, very close to the base station, and you're receiving a lot of signal. So you should be able to do that recognition on the fly. So these are the Radio ML 2016 data set. And there is a Radio ML 2018 data set where they use a digital source called the Gutenberg works of Shakespeare in ASCII format that digitize that voice signal and modulate that signal and transmit over the wireless, digitize it and save it as a data set which you can download from the website. And there have been a lot of work. These are the early works in 2016. I think it was a DARPA research that came up, Radio ML. How do you figure out modulation schemes automatically? And nowadays, I think the LTE modems that are coming out this year will have AMR built into them. They are having AMR built into them. So that's a very nice area to be in at this point. So what people have been doing is, this is the conventional RF receiver. So there is an LNA, there is a mixer, filter, ADC, then the demodulation is sitting here, which figures out what bits are, right? So these don't know what the bits are. They don't know anything about what information is there. This I and Q signal goes to the demodulation. That figures out if it's an image, if it's a voice, if it is whatever it is, right? So what we do is we interpose a modulation recognition block over here, and this takes in this signal and figures out what kind of a modulation it is. So this is what people have been doing. As you can see, this block has been operating at a sample frequency much higher than the frequency at which the receiver is supposed to operate. So that means higher the frequency, more the power consumption. So, but if you go to the, right, what we have proposed, and this got published this year, we are presenting in ISCAS conference 2025. So what we have is we are using a very low resolution quantizer followed by a modulation recognition that is operating at 1/16th the sample rate of the whole receiver chain. So that means it's operating at a very low frequency. So that means it saves significant amount of power. So now this is if you look at an RF signal, it's a stream of bits. It's not an image signal. So what we do is we convert that stream of bits into an image by converting it into a two-dimensional I in one direction. So I is in-phase signal and Q is the quadrature component of the signal. These are that's how you transmit signals on the RF side. So I is the x-axis of the image and Q is the y-axis. And we convert that into image. And based on the bits that are coming out, we will say if it is a white pixel or a black pixel. So it's a 1-bit quantization, 4-bit, but it will have some grayscales over there. Actually, it is 1-bit because we are doing it, representing that as spikes. And the dimension of the I and Q is the number 2 to the power of n, which is n is the number of bits that the ADC gives out. So if I digitize to 12 bits, you'll have 4096 X and Y. So that's a huge amount of data. So we saw that 4 bits gives us the optimal number. Then there is a leaky integrate, LIF stands for leaky integrate and fire neuron, because this is a spiking neural network. So there are 2 layers of a network, then a fully connected LIF neuron. So I am not getting into the details of how we implement the neuron. The neuron is also implemented actually in analog domain using something called an oscillator. So I won't get into that. So now the conclusions that we obtain are that based on all the simulations, you can see SNR is on the x-axis, accuracy is on the y-axis. And what we find is that and it can recognize modulation all the way down to -6 dB of SNR. SNR stands for signal to noise ratio. And typically for almost all cell phones and all, -6 dB, 0 dB SNR is good enough for making sure that you can receive a signal. If it goes below that, then signal starts dropping off, you lose the signal and all. So we need 16 frames, and n equal to 4-bit gives us the optimal resolution. And based on our thing, we compared with previously published work, we are approaching, I cannot point to, we are approaching the whatever is the state of the art with this thing. And can we place this video, please? So we have, this took 2 months of work to get it to work. Yes. So this is how the modulated signal looks like if you monitor it on a spectrum analyzer. It looks like a band of signal, and the carrier is right there. And we chose 1.8 gigahertz because that is the CDMA band. Most of the cell phones work at 1.8 gigahertz and 900 megahertz. In the US, I think is 1.8 gigahertz. In Asia and all, it's 900 megahertz. So, so this work actually took a while because it involves 4 things to make it to work. One is the DDR interface, which is a memory block that is there inside the board. Then there is a processor inside because it's an RF SoC. So there is a processor and the logic, which is a FPGA. So we had the DDR to processor, processor to logic, logic to DAC, DAC to ADC, back into the logic, back into the processor, and do all the more. So we are trying to build an ASIC that can do all the things, everything together. So that work is in progress. We just made the chip, which is in Global Foundries 12LP process. Should be getting back the chip in November, and we can demonstrate the whole thing on the chip right there, but all 24 classes of modulation, that's a goal. So overall, I'll conclude with this thing. Wide range of hardware solutions are there. Early days, CPUs, move to GPUs, TPUs, GPUs, TPUs are almost a similar thing. Now people started doing FPGAs, now moving into specialized ASICs. Mixed signal ASICs hold a significant promise. Each architecture offers unique trade-offs in performance, power efficiency, and flexibility. 2 FPGA solutions presented that are related to edge inferencing. I presented 2 FPGA solutions. Application-specific optimization is the key. So you need to really find out what operations are happening and how to optimally configure the hardware to make sure it happens. So that it becomes like, I think I say that it actually becomes a software hardware co-design. So it is not just a person who writes a CNN, but also if the person who is writing the code using PyTorch or whatever, TensorFlow, if he or she is aware of how it is going to get realized on the hardware, that will make it really easier to translate. And there is a lot of work already happening in that. VITIS is one of the high-level synthesis language that enables that to some extent, not to the great extent yet. So now we have neuromorphic computing that is also coming, and then analog processing as a potential game changer. For example, we can do matrix multiplication at a much, much faster rate in analog domain. It is not very accurate. It is 8-bit accurate, but it does in a flash. So now the thing is that can that be used as an accelerator further to your digital block? A coarse acceleration followed by a fine acceleration by a digital block, and then a software takes over after that. So it's a 3-way solution that can become up. So, and especially with CMOS plus X stands for anything on CMOS on top. There is another novel devices that are coming in that can enable this. Now we are looking into this. Last year, 1-bit LLM came out, 1.58-bit LLMs have come out. So we are working on a hardware to build a 1-bit LLM thing. And in fact, it can be done. We are doing it for RFML also, radio frequency ML, using the first stage of our radio receiver. I'll just take 2 more minutes to go back here, is a mixer here. A mixer is nothing but a multiplication block that multiplies with plus minus 1. And a 1-bit LLM, all it needs is 0, plus and minus 1. And I think we can do the detection right here. We don't even have to go here to this point. So let's say whether we can get that. So that is one of the hot areas. And so you can do it in digital domain as well, 1-bit LLMs, all additions and all. So I would say there is now, I think besides all the boom that is happening, I think the hardware aspect has a lot of potential that we can explore. And one more thing I want to conclude is that the rental implant, the images that you have shown, I think we can leverage our work that we did on image compression using INR, possibly if we can get the hardware to work. I had that idea that can we use those for medical imaging and really build energy efficient imagers, which are portable devices the doctors can carry to remote places and not have to worry about a power wall outlet to take images and store them and all. Any questions? Sorry, it took 4 minutes more. So.
No, you were on time. So yeah. Any questions?
So I don't know if at the first of your presentation, so I missed some kind of things that you said, but okay. So the thing is, so the idea is to optimize so the bandwidth, right? That's pretty much in terms of the the number of pixels. So perhaps my question is some kind of also confusion because it is supposed that all the time, so we are implementing so modulations because as you recall, so when we started so with the cell phone AMPS technology, then CDMA, so with so these higher bandwidth, so now so we have optimized so the bandwidth. But so why, in certain way, so we would like to so reduce the resolution It is supposed that it has to be higher resolution. Oh yeah, of course. So the problem is higher resolution, higher bandwidth. But I don't know if I am kind
No,
of
no, no.
confusing
Actually,
that part. Can you explain me?
I got your point, what you're saying. So basically what you're saying is we are putting a very low resolution quantizer in the RF chain, right? RF receiver. So this is just for modulation recognition. The main signal reception, if you are going for 16 QAM, 32 QAM, 64 QAM, 256 QAM, this one has to be in the main receiver, which actually figures out your bits, has to be 8 or 12 bits. It cannot be without that, because you cannot make now modulation recognition is not recovering the information from the signal. It is only recovering the scheme of modulation, right? So, and after you recover the scheme of modulation, you turn off the block and you operate the regular way. So that means this block, I would say there will be a splitter over here that splits out, and that goes here and gives you 12 bits and gives you the demod, goes to the demodulator, actually figures out the bits. So that's why people typically use 8 to 12 bits. 8 bits if it's a very wideband receiver, because you know that if I have a very wideband receiver and my signal is in a narrow band, I have processing gain on it. So I can, with 8 bits is more than enough. The TV tuners that we worked on, the TVs that you're watching right now, all the TVs, digital TVs and all, they have an 8-bit ADC in there. And they capture close to 2 gigahertz of signal right there. And then they channelize it and give you channel number, Fox channel, CNN channel in the digital domain. So that digitization is happening at 8 bits. That you cannot reduce because you have to recover the information. But the modulation recognition doesn't need to recover the information. It has to just say what kind of modulation it is. So that's where you need low resolution ADC. Sorry?
Actually, stick with the phone recognition.
Yeah, modulation is a recognition, and the receiver actually does a detection. Yes, it does a detection of the signal. Yes.
Any other?
The video, the modulation recognition.
I didn't know.
I actually talked to you, okay? Because there's an actual competition on this one.
Oh,
Yeah.
we have working. We actually.
That's what I'm saying, yeah.
I think can I switch it off?